All right, so welcome this morning. I hope everybody is doing well. If you haven't logged into Learning Catalytics, go ahead and do that. The first question that well, it's not a question yet, but the first thing that I want to cover with you this morning are some naming conventions, and then I'll ask you a question to see if you kind of have this idea down. A general first order differential equation is one of the form dy dt equal f of ty. So the left-hand side here is the derivative, y is the dependent variable, t is the independent variable. The function on the right-hand side tells you a slope at every point in the plane. So basically what you're doing is you're creating a vector field. For those of you that know what a vector field is, a differential equation creates a vector field that we call a slope field for this course, and we'll talk about that more on Wednesday of next week. But for first order differential equations, depending on what this function on the right-hand side looks like, it's called something different. So if the function on the right-hand side is just a function of time, then in other words, if your slope in the plane depends only on time, then your differential equation is called a pure time ODE, or ordinary differential equation. If the function on the right-hand side depends only on your basically y value or dependent value, then it's called autonomous. The word autonomous comes from the word autonomy, which means freedom. So this is free from time is how you should think of it. So an autonomous ODE is an ODE whose right-hand side, when written in this form, is free from the time variable or the independent variable. If the right-hand side can be written linearly in terms of y, then it's called a linear ODE. So it doesn't mean like constant, like a, it doesn't have to be constant. It's not ay plus b. These could be functions of the dependent variable, but if the right-hand side were is linear in terms of y, so this looks like a linear function, right? You've got a slope times y plus an intercept, but these are functions of time. If you're linear in the dependent variable, then you're called a linear ODE. If you can't write the right-hand side linearly like this, then your ODE is called nonlinear. The last two terms to talk about here are the order of a differential equation. The order of a differential equation is the highest derivative of the dependent variable in the equation. So this is called a first order differential equation because y has only one derivative being taken. We will look at in this course second, third, and fourth order differential equations as well. Because in the real world, first, second, third, and fourth order differential equations actually have a good bit of physical meaning. Once you get above fourth order, you start to lose physical meaning. There are some examples of higher order differential equations that matter for applications that we're aware of, but not too many above fourth order. The dimension of a differential equation is the number of independent variables. Since this is ordinary differential equations, we will always have one independent variable. It's usually going to be time. In partial differential equations, we will have at least two, sometimes three or more independent variables, which makes those problems partial derivatives instead of ordinary derivatives. So I just want to see if you picked up on some of the notation here. Let me give you a question related to this. So here we have a differential equation that's written for you, and I want you to tell me which of the following correctly gives the name of this differential equation.
Can you go back up to the code?
I can, yeah. There you go.
Thank you.
All right, so everybody that's currently logged into Learning Catalytics has answered. More of you can filter in and log in if you need to. If you want to participate, even if you don't have Learning Catalytics set up, you can always go to learningcatalytics.com/demo, like we did in class on day one. And when you're in there, you can participate, but it won't save your answers. All right, so we were a little bit off on this one. And that's why I wanted to look at this example with you, because I think one of the hardest things for students to recognize is linear versus nonlinear. So let me jump over to my iPad real quick here. And let's talk about it. The differential equation that you were given here was dy dt plus 2t divided by y equals 4t. And if it's going to be linear, then I have to be able to write it in the form dy dt equals a times y plus b. In other words, this has to look like a linear function of y, right? Here, the a and the b. So a and b could be functions of t, right? They could be a of t and b of t, but it has to be linear in terms of y on the right-hand side. So I want to try to write this one in that form and see if we can put it in that form. So if you rearrange things here, you'll have dy dt equals negative 2t times 1 over y plus 4t. So the question to ask here is the function 1 over y, is that a linear function in terms of y? And the answer is no, it's nonlinear. I can't make this look like this form. So this is, in fact, a nonlinear ODE. Okay? So if you answered linear, I just want to make sure you understand why this one is nonlinear. Basically, the things that you can't do to y, you can't square it. So if you see a y squared in a problem, or whatever the dependent variable is, if you see the dependent variable squared, you can't do that. You can't raise it to powers. You can't have like y times y prime. Like that will never work. You can't have square root of y. That's not linear. That'll never work. You can't have y inside another function like sine of y. That won't work. So all of those things are nonlinear. And the importance of linear versus nonlinear in this course is if a differential equation is linear, it always has an answer, and that answer is easy to find in this course. If a differential equation turns out to be nonlinear, I can't promise you, for one, that it has an answer, at least that we can write down. We can always look at its slope field or its solutions and done numerically, but the chances of us being able to write down a solution for a nonlinear ODE are not good. And then solving them it's a juggling act. I mean, you never know what kind of nonlinearity you're going to run into, and the chances of being able to solve it aren't usually all that good. So just want to make sure that we also understand the other two parts of this don't apply. So pure time, this is definitely not pure time because you do have y on the right-hand side. It's also not autonomous because you have t on the right-hand side. So this is a function on this right-hand side, a function of both t and y, so it's neither pure time nor autonomous. Okay. So let's try another question, kind of similar, but here I'm going to throw a second order differential equation at you. Or maybe it's a first order, or maybe it's a third order. The point is you have order as a part of this as well. So you'll have to decide, is it first order linear, second order nonlinear, etc. All right, got about another 20 seconds or so to enter an answer. Let me know if anybody has any technical issues or anything like that, if the audio is not coming through clearly. All right, so from your responses, second order linear is correct. Those of you that said nonlinear, this may be a bit of recency bias from the last question, but I want to show you once again why this one is linear, whereas the previous one is nonlinear. But the first thing I have to do in order to do that is make sure that we understand how the notion of linearity basically changes as we get higher order. So for starters, I know that this is a second order ODE because I have a second order derivative of y here. So I know right away it's a second order differential equation. We said before that you were a linear ODE, in this case of first order, if you could write, say, y prime equal ay plus b. And remember, this is where a and b are possibly functions of an independent variable. Well, what this would look like for a second order ODE is you would have y double prime equal to linear in terms of y is also linear in terms of y and its derivatives. So this would be something like, say, ay prime plus by plus c. That's what linearity would look like for a second order differential equation. So if you want to think of this as being quadratic, I guess you could, but it's linear in terms of y. The definition of linearity for mathematics is a function is linear or an operator is linear if it has the following property. You can distribute to each piece, and you can factor out any constants. So if you're unable to do both of those things with whatever operation you're using, it's not linear in mathematics. So you can see over here on the right-hand side, if I have a function for y, say y is 2e to the x plus sine x. Maybe that's my solution, right? You can see that if I plugged that in for each of these things, it obeys these two properties. When you take the derivative of something, the derivative distributes to each piece and it obeys these rules. So having the derivative there is not a big deal. If you had a constant times y, you could just take and multiply the constant onto each piece, and it splits apart nicely. Square roots don't obey this. Like if I was to take the square root of y here, I can't split underneath a square root. So it's not a linear operation at that point. So the way a second order differential equation is linear is if its right-hand side can be written this way. So taking this differential equation that we have and writing it in sort of this standard form where I take everything but the highest order derivative and put it over on the right-hand side, we would have y double prime plus, y double prime equals negative 2x y prime minus 3y plus e to the negative 2x. I'm then going to divide by x squared. So if I divide by x squared, I would get minus 2 over x, y prime, minus 3 over x squared y, plus 1 over x squared e to the minus 2x. And if you look, that right-hand side is a function of x times y prime, plus another function of x times y, plus a third function of x. And that matches the form that I have here for linearity. So this is indeed a linear differential equation. It's a second order linear differential equation. Do we have any questions about that? Because the difference between linearity and nonlinearity is something we're going to want to be able to recognize this semester.
Yeah, you explained it really well here. I just had no idea about like what to do with the x. I just saw that the x squared is multiplied by the y double prime and was like, that doesn't look like it can be linear.
Yeah, it's linear. You always, when you talk about linearity, you ignore the independent variable completely. So x is the independent variable here. We ignore that. Linearity refers to how the dependent variable is handled in the problem, because the independent variables are simply they simply act as constants in a sense, like they get multiplied or distributed to the dependent parts once you plug in a solution for y. So the way that it's written here is linear. And it's because it satisfies these two properties. You can pull out constants and you can distribute the operation to each piece. Those two things are needed to be linear. Okay, so let's keep trucking along. All right, I'm gonna solve some differential equations now with you, but the purpose of solving these is to talk about what's needed to solve what's called an initial value problem, or an IVP. So there's nothing to respond to here. I'll let you respond to a question, follow up here in a second. I'm going to do two simple equations to start with. So the first of these equations is, well, you can probably tell me what it is here, but it is y prime equal to 2x. This is a pure time differential equation. Pure time or pure value because x is the independent. When I write it this way, it's the same as writing it this way, right? So oftentimes we won't do that. We won't write it both ways in a problem. Just understand that when I write y prime, because I see x elsewhere in the problem, I now know that's y prime of x. I'm taking the derivative with respect to x. So x is the independent variable there. So solving this is a matter of, honestly, this is almost Cal 1. This isn't really a differential equation for ODEs. This is more of a Cal 1 or Cal 2 problem. The goal of solving a differential equation is to find, so I'm trying to find the unknown function y that satisfies both sides of the equation. That's the goal in this course. Sometimes it's easier said than done. It's really easy on this particular one because I'm looking for a function whose derivative is 2x. So basically what I'm asking you about is, what is the antiderivative, or I would take the integral of both sides to solve this. So on the left-hand side, the integral of y prime dx is just y. And on the right-hand side, the integral of 2x, or the antiderivative of 2x, is x squared divided by 2 times the 2 that's already there. So you would just get x squared plus a constant. One of the important things that you learn when you solve differential equations is you will often get a family of solutions. In fact, it's almost always going to be an infinite family of solutions. There's not just one answer to this question. There are an infinite number of answers to this question, because there are an infinite number of curves in the plane that have the property that their derivative at every point is given by 2x. How do we focus on the one answer that we care about? Well, I need more information. If you want to pin me down to a single answer, I need more information. So in the problem that's given, you're also told that y of 0 is equal to 7. This is called an initial condition. And the purpose of this initial condition is giving you more data to figure out what C is. So if y of 0 is 7, y of 0 would be 0 squared plus C is 7, which tells me that C is 7. So my explicit solution would be y equal x squared plus 7 is the answer to this differential equation. And the reason that it's the answer to this differential equation is if you take that solution and plug it back into the differential equation, it ticks all the boxes, right? So what's the derivative of x squared plus 7? Well, it's 2x. So 2x equals 2x. Good. That works out. Does it also have the property that at 0, it's equal to 7? Yes. Therefore, it's the only answer to this problem, which we call an initial value problem, because it involves both a differential equation together with an initial condition. All right, let's make that a little bit tougher by looking at a second order differential equation and the IVP associated with it. Say y double prime equal 2x minus 4e to the x. Now, the initial value problem that you have written in Learning Catalytics looks like this. And the question is, well, why do I only needed one initial condition here. Why do I all of a sudden need two initial conditions here? The reasoning behind that is because I have a second order differential equation, I'm going to have to integrate twice to find y. And in doing so, I'll create two integration constants. And if I want to solve for those two constants, I need 2 points of data, not just one. And I need a point of data for every derivative under my order. So if I was to give you a, kind of down here, if I was to give you a fifth order differential equation, which we're not going to do, it would be a function of x, y, y prime, y double prime, y triple prime, and the fourth derivative of y. All of those things could show up. But if I'm going to give you an initial condition, I've got to know the value of y at a point. I've got to know y prime at a point. I've got to know y double prime at a point, y triple prime at a point, and the fourth derivative of y at a point to be able to solve something like that. So as you increase the order of a differential equation, you need more initial conditions to be able to pinpoint the exact solution that you're interested in, which obviously becomes messy. But for the second order one, if we just take the antiderivative of both sides, we'll do it once with respect to x. So y prime is equal to, let's see, the antiderivative on the right-hand side is x squared minus 4e to the x. Now, I've produced an integration constant on both sides. But if you remember, we had a conversation about this on the first day of class. There's no need to write a plus c and a plus d here because they're both arbitrary constants. All I need is one integration constant in the problem. So this first constant that shows up, I'll call it C1. This first constant that shows up is attributed, the data for finding it is attributed to y prime. And we have a y prime condition here, y prime of 0 equal -1. So we can plug that in to find C1. And so C1 is 3. So now I know what my y prime of x is. Like I said, this is nothing more than a calculus 1 problem, okay? I'm not doing anything fancy here that you haven't probably seen before. I just want to make sure we understand the connotation of it in this course. So I'm going to take another derivative with respect to x, or another antiderivative. The antiderivative of y prime is y. Antiderivative of x squared. Antiderivative of 3 is 3x. and then I produce my second integration constant. So here I use the final piece of data, y of 0 is 2. If you use that, you'll plug in x equal to 0, so you'll have 0 cubed over 3 minus 4e to the 0 plus 3 times 0 plus c2 is 2. Or, let's see, that's minus 4 plus c2 is 2. So c2 is 6. So the correct answer to this differential equation is this. In other words, this is the only curve in mathematics who has this for a second derivative that passes through the point 0, 2 and has slope -1 when it does so. That's what we've been able to find here. Now, if this was all the course was, then it's nothing different than what you've done in calculus before. What makes this course trickier and more difficult than calculus problems is, what if the derivative depends on y? In other words, what if there's a y over here on the right-hand side? Then all of a sudden things become much more difficult, and very few of our calculus techniques carry over for handling that situation. So this is what an initial condition is. The important thing to get out of these two quick examples are that you need as many initial conditions as you have order of your differential equation to be able to solve it. So if you have a third order differential equation, you need 3 initial conditions. All right, so follow-up question here. I've given you a function, and I want you to tell me, is this function a solution to this initial value problem? We feel reasonably good that this problem can be solved because it's linear and because it has one derivative and one condition to go along with that derivative. So we feel good that we have enough data to solve the problem. It's just a question of whether or not this is the correct solution. And I'll give you about another 30 seconds or so. And maybe a minute. All right, if you haven't committed to a response, you should do so immediately. Right, so here we go. 63% of the class. I don't know how that works out. Oh, I guess it rounded it up. Okay, it added up to more than 100%. I was confused at first, but I guess it just rounded up the values. So 63% of y'all said true, which is correct. Let's take a look at it. So what does it take in order for something to be a solution to an initial value problem? Well, our candidate for the solution is 2e to the minus 2t plus e to the t. For this to be a solution, I have to be able to plug this in everywhere I see a y. And both sides of the equation should be equal to each other, okay? That's the first thing. I have to be able to plug it in and satisfy the equality. Then I have to also check, does it satisfy the initial condition? So there are two checks that need to be made here. So the first check is I'll take the differential equation and I'll plug in my proposed solution. And I'm going to check on both sides. So the derivative of 2e to the negative t is negative 4e to the negative 2t. The derivative of e to the t is e to the t. Distribute the 2 here. You'd get 4e to the negative 2t, 2e to the t. The negative 4, positive 4 cancel. E to the t plus 2e to the t is 3e to the t. So that part checks out. It satisfies both sides of the equation. All right, if I then take and look at the value at y at 0, this is 2 times 1 plus 1, which is 3. That also checks out. So not only does it satisfy the equation, but it also satisfies the initial condition. Therefore, this is considered a solution. We call solutions to initial value problems, we call these particular solutions. So this is called a particular solution because it's one of those infinite number of possible solutions that we could get out of this thing. It's a particular one of those. So a solution to an initial value problem is called a particular solution. Solutions like this one that are infinite families, those are called general solutions. So this is a solution in general because it could work for many different initial points, but I don't have a specific one in mind. So are there any questions about how to check whether a solution satisfies the differential equation? Obviously, as the equations get more complicated, you'll have to do more work to check, but this is how we check to see whether or not it satisfies the differential equation. All right. So kind of an unrelated question, but just seeing if you're picking up on the structure of a differential equation here. I have a way more complicated differential equation than anyone we've looked at so far, but the good thing is I'm not asking you to solve it. All I'm asking for you to do here is tell me what is the slope of solutions that pass through the horizontal axis. In other words, if you have a solution to this differential equation passing through the horizontal axis, what is its slope? All right, you got about 30 seconds. All right, so here are the answers from everybody, and looks good. 56% of us correctly said that the slope was 2. Let's talk about where that would be coming from. So, you know, the goal for today is get you comfortable with notation, what a differential equation is, kind of what it says, some of the naming stuff. The best way with a first order differential equation like this one to think about it is to always write it in that standard form from the beginning. That is, put the derivative on one side, put everything else on the other side. That'll help you understand a little bit better about what's going on. So if I do that, dy dt is equal to, let's see, you're gonna add t cubed y over, and then you're going to divide through by t squared. So in standard form, this differential equation is ty plus 2. Okay? So there's the differential equation you have. Because t and y are both present, the independent and dependent variable are both present on the right-hand side, this differential equation is neither autonomous nor pure time, so I can't easily solve it. It is linear. We'll learn how to solve linear equations very soon. The question that's asked is if you pass through the horizontal axis, so the horizontal axis is where y is equal to 0, right? So if you're passing through the horizontal axis, y is equal to 0, this function f of ty, it tells me the slope at every point in the plane governed by this differential equation. In particular, if I'm talking about along the horizontal axis, then I'm asking this function what its value is when y is 0. So f of t comma 0 would be t times 0 plus 2, it's 2. So all of the slopes along the horizontal axis are 2. I'm going to bring Maple over here in a second. We're actually going to look at this problem in Maple and see that that's indeed correct. But I want to reverse the question for a second. I want to ask instead, what if we wanted to know everywhere this ODE has slope 2? Well, the way the differential equation is written, I know the right-hand side is the slope. So I'm basically saying take the right-hand side and set it equal to 2, right? Well, if you solve for y, what do you get? You get y equal to 0. So only along the line y equals 0 do we have slopes of 2. So the question could be asked to you either way. I could say, here's some specific curve in the plane. What are the slopes along that curve according to the differential equation? Here's a slope in the plane. What curves have that slope? Right. Now, taking a look at this in Maple, I think is going to be instructive for us. We're going to get into more Maple stuff this next week in the class. But I'm just going to start by writing down the differential equation. So our differential equation, and I'll even write down the original one here. So the original differential equation, I'll just call it ODE. So this is how you name things in Maple, ODE, colon, equal. So I'm gonna call the differential equation here ODE. And it is t squared times the derivative of y with respect to t. So that's the derivative of y with respect to t, minus t cubed times y. Now notice that every time I have the dependent variable y, I'm writing it as a function. You shouldn't just put y. Okay, this is one of the mistakes that I see students make most often. You can't just enter y, because y is a variable, y of t is a function. The solutions to differential equations are functions, not variables, okay? So this is y of t, and then it equals 2t squared. So there's my differential equation. One of the first commands you learn is dsolve, which is take and solve that differential equation. And it looks horrible. This is not an equation that you would want to solve by hand necessarily, although it's not too bad once you write it in the proper form. But this allows me to solve that differential equation for y of t. Notice I do have a constant here, C1. That's an arbitrary constant, which I could find given an initial condition, but we don't have an initial condition here. So one of the commands that we'll talk about next week is something called DE plot. Now this is a package, so you load packages in Maple. These are all the commands that come with this package. We will not use all of these this semester, but one of the commands that we will use often is DE plot, both the regular and 3D version of it. So by loading this package, the colon at the equal of it suppresses the output, okay? So by loading that package, I have access to that DE plot command. And what I'm gonna do is plot that differential equation. Y of t is the variable, or is the function variable. And I'm gonna plot it, let's say from t equal minus 10 to 10, y equal minus 10 to 10. So I'm just giving it an axis to plot on, okay? Well, you can see here that this is the vector field that this differential equation creates. We call this a slope field. What this is an arrow. The computer is drawing an arrow at each point in the plane that I've specified, and the direction of that arrow comes from evaluating the right-hand side of the differential equation, f of ty, at every point t comma y in the plane. I'll make the arrows look a little bit better. There's all sorts of options that come with this. That's my favorite one because it actually looks like an arrow rather than a little harpoon. But we just got through talking about at y equal to 0, as things cross through the horizontal axis, they have slope 0, or slope 2, excuse me. You can kind of see that here, right? As things pass through the horizontal axis, you can see coming in here, coming in over here, things have slope 2 as they pass through. Now, that's going to be something that we're going to explore way more in depth this next week. We're going to start to use Maple more and more. If you haven't gone and looked at the Maple lecture files, Maple Lab Lecture 1 and Maple Lab Lecture 2, you need to do that before Monday's class, because we'll start to get into more of the concepts that we would have normally talked about in a Maple Lab but are talked about in those videos. You need to try and get comfortable enough with Maple that you can do exactly what I just did here. You need to be able to write down a differential equation, store it to some name. You need to be able to use the dsolve command like I've used here, and you need to be able to use the DE plot command. So that essentially is your homework for this weekend, is to go in and familiarize yourself as much with Maple as you can, and being able to do these 3 commands. Let's see, I think we get out of here at 11:10 normally, right? No? Yes, because it's 10:20 to 11:10, okay? So there is one more question that I'll throw out at us here for the last 2 minutes of this session, and then we'll call it a weekend, or call it a week. if you write the differential equation in the form dy dt equal f of ty, then any constant solution that makes the right-hand side 0, you're making the slope 0. And if you make the slope 0, oh yeah, Wyatt, I saw your thing about the math VDI. We're currently working on it. What happened was we had 2 different programs that were using the same port output. Maple was one of them. So they had to switch it to a different port so that you could get access to it. But the VDI should be up and working. Honestly, it should be working really soon. If it's not working by later today, let me know, okay? Because they told us they knew what the issue was, and they were going to get back to us for it. But if you can, go in, take a look at some of that stuff this weekend. In terms of an equilibrium solution is a constant solution that makes the right-hand side 0. And if you make the right-hand side 0, then you're saying that the solution value y no longer changes because its derivative is 0. So if you have a derivative of 0, you have no change. So what I'm asking for here is, are there values of y that make the derivative 0 that count as what we call equilibrium solutions? We'll talk a lot more about this in 2 weeks, but I at least wanted to throw the term out at you today. So which of these answer choices is an equilibrium solution? You've got about 30 seconds for this. I know that's pretty quick, but I don't want to keep us over time. All right, you got 10 seconds. I know that might not have been enough time, but you got 10 seconds to respond. All right, correct answer is A. Only y equal to -1 works. So an equilibrium solution is a constant value of the dependent variable that makes the right-hand side 0. If you plug in y equal to -1, this factor goes to 0, so the right-hand side goes to 0. That means not only is y equal to -1 a place where the slope is 0, it is also a solution. Because if you plug in -1 to the left-hand side, the derivative of -1 is 0. If you plug -1 into the right-hand side is 0. So it is what we call an equilibrium solution. A lot of you chose E as well. What I'll say about E is y equal to 3. If you plug y equal to 3 into the bottom here, you're dividing by 0. So the slope is undefined. That would mean that the slope field that we looked at earlier, you would have a vertical line at y equal to 3, not a horizontal line, okay? So that would be a place where the slope field is undefined, not a place where you have a solution that's in equilibrium. Equilibrium implies no change over time, so you have a horizontal solution at that point. All right, I threw a bunch of terms out at you today. You may want to go back and review this recording and read through the first 2 sections of the textbook, section 1.1 and 1.2, in preparation for Monday. Throwing a lot of terms out at you now. We're going to kind of slow down that a little bit and start looking at individual topics from here on out. But this was kind of just throw a bunch of terminology out at you and kind of give you a little bit of an introduction to some things for the semester. Y'all have a great weekend. Hope this went well. Let me know if it didn't. See y'all later.